Alright, let's start the next video. Find the Z transform and ROC of the following signals is the next question. And the first sub-question is x of n equal to 2 power n u of n. Okay, so we have to find the Z transform and ROC of the signal x of n equal to 2 raised to n u of n. So we will start from the scratch, I think. So given x of n equal to 2 to the power u of n, therefore you know the Z transform is obtained by n equal to 0 to infinity. I'm giving n equal to minus, not giving minus infinity to infinity, but from 0 to infinity because the signal is being truncated by u of n. So it's only a right side of the signal. Okay, you know this. So x of n into 0 raised to minus n. Now we will apply specifically what x of n is. So sigma n equal to 0 to infinity 2 raised to n into 0 raised to minus n. That's somewhat I can write it as 2z inverse to the power n. Okay, 2z inverse to the power n is 2 raised to n z inverse n. Okay, now the only way before us to proceed is to expand that sigma, right? And that will give you, that is equal to, if you could put n equal to 0, 2z inverse raised to 0, that will be 1. Plus for n equal to 1, it becomes 2z inverse. For n equal to 2, it becomes 2z inverse 2. Oh, I'm sorry, 2 raised to 2z inverse 2, fine. So I can write as 2z inverse to the power 2 plus 2z inverse to the power 3 plus etc. and goes to infinity. Okay, so this is, as you know, this is a GP, infinite GP, whose sum can be written by the formulas Sn equal to a by 1 minus r, where a is the first term and r is the common ratio. So in this GP sum, you can see a equal to 1 and r equal to 2z inverse, right? To find r, you just divide one term divide by the previous term. So dividing this term divided by this term will be the simplest to do. So that will give you 2z inverse. Alright, so I can convert this sequence to 1 divided by 1 minus 2z inverse, because a is 1 and r is 2z inverse. Okay, so that is the answer. But you know, because it is Z transform, you cannot just stop finding the Z transform here, but ROC is also the important thing. So what is ROC? You know how to find out ROC because we have done a very important assumption here, because we can use this equation only if this r is less than 1. Modulus of r is less than 1. So from that assumption, here the modulus of r is 2z inverse, right? So modulus of r less than 1 means mod 2z inverse is less than 1. That means mod 2 by z is less than 1, or mod z is greater than 2. That's what we are getting from this inequality. So ROC is mod z greater than 2. So that completes part A of this question. And now we can move on to finding the answer to the question B. That is very simple. They are asking the Z transform of del of n, which you know it is 1. For any Fourier or any frequency domain representation, whether it is DTFT, be it is DTFS, Laplace transform, or Z transform, whatever be the transform, del of n will give you 1 in the frequency domain. Okay, del of n or del of t always give 1 in the frequency domain. So here x of z is equal to sigma n equal to minus infinity to plus infinity. X of n into 0 to minus n becomes del of n into 0 to minus n. Okay, and from the property of impulse, we can say that this as sigma n equal to minus infinity to infinity. The second function 0 to minus n converges to the only value where del of n exists. And where does del of n exist? Del of n exists at n equal to 0 alone, right? So this 0 to minus n comes to 0 to minus 0, right? Del of n exists only at n equal to 0. So 0 to minus 0 into del of n, but 0 raised to minus 0 is 1, and there is a constant. I can take it out. So sigma n equal to minus infinity to infinity del of n, which by definition you know it is 1. So this is 1. So that's how you can prove that the Z transform of del of n becomes 1. Okay. And ROC, what is ROC? ROC is the entire Z plane, right? Because Z transform is just a constant, 1. 1 is stable everywhere on every plane, every part of the plane. So ROC is the entire Z plane. Entire Z plane. So that completes the answer. And the next question is, Paul 0 plot for Z transform x of z of a discrete signal x of n as shown below. Determine the ROC in each of the following cases. First one, x of n is right-sided. Second one, Fourier transform of x of n converges. And third one, x of n is left-sided. Please don't be afraid of seeing this bulkiness of this question. This might be probably the easiest one in the series because you know what you have to do is to determine ROC. Okay, the question is all about determining ROC for 3 special cases, and what you are given is a Paul 0 plot. Okay, it's more than enough. So you have to find out the ROC for 3 special cases. The first one is x of n is right-sided. So let me redraw this Paul 0 plot for convenience. Okay, so this is our Z plane, and I have shown the Paul 0 plot. You can see one pole is at 2 by 3, another pole is at 2, and I have drawn a circle corresponding to the pole 2 by 3 and another circle corresponding to the pole 2, and also this yellow color circle is our unit circle in the Z plane. Okay, now let us see what is the ROC. Just mark the ROC in this particular Z plane, wherever it is, for first question, x of n is right-sided. This is very simple because x of n is right-sided means what should be the nature of its ROC? What should be the nature of the ROC of the Z transform of this right-sided signal x of n? It should be, ROC should be outer to the rightmost pole. Outer to the rightmost pole. Outer to the rightmost pole of the Z transform. Which is the rightmost pole of the Z transform? That is nothing but 2. So you can see it a circle on the pole, circle bounded by the pole 2. The ROC should be, for x of n to be right-sided, ROC should be right side or outer to the outermost pole or rightmost pole. So I can draw the ROC as this entire plane, entire region outer to the outermost pole. So this region could be the ROC. Okay, so that is the answer to the question A. Now for question B, they have asked to find the ROC if the Fourier transform of x of n converges. Discrete time Fourier transform of x of n converges. And what does that mean? I invite your attention to the previous video, just part 22 of a video, or part 21 of the video, which establishes the relation between DTFT and Z transform. DTFT is nothing but Z transform evaluated along the unit circle. We proved that using the Z transform and DTFT equations. I request you to, if at all you are not familiar with this idea, I request you to watch the previous 2 videos, part 21 and 22 of this video series. And or else I can have a quick review, because Z transform equation is sigma n equal to minus infinity to infinity x of n into z raised to minus n. And what is z? Z is a complex number, r e raised to j omega in the polar form. And if at all I'm taking mod z equal to 1, right? If at all I'm taking mod z equal to 1, what I end up with is I can rewrite this x of z with mod z equal to 1 restriction as x of z equal to sigma n equal to minus infinity to infinity x of n into, instead of z raised to minus n, I can write e raised to j omega whole raised to minus n, because as mod z equal to 1 becomes r equal to 1. Okay, mod z equal to 1 turns r equal to 1 because r is the magnitude equal to 1. Okay, so e raised to j omega to the power minus n, or I can write it as e raised to minus j omega n. Okay, and what is this equation? This equation is nothing but DTFT. Okay, DTFT. So we can conclude that DTFT is nothing but Z transform evaluated along the unit circle. Mod z equal to 1 means it is a unit circle in the Z plane. Okay, so the question asked us to find the ROC if at all the Fourier transform of x of n converges. Fourier transform of the x of n converges means the Z transform should be such a way that its ROC should contain the unit circle, right? If at all the ROC contains the unit circle, DTFT exists and converge. Okay, if at all the ROC of Z transform contains the unit circle, DTFT exists and converges, right? Exists. So our aim is to find out a possible ROC from the Z plane, find out a possible ROC from this Z plane, so that ROC contains the unit circle. ROC contains the unit circle. Okay, so our aim is to identify a possible ROC that contains unit circle in the Z plane. So what can be that? For that you have to go through a small point in ROC properties. One is ROC cannot contain pole. Or in other words, an ROC will be bounded by poles, right? ROC is bounded by poles. Okay, the second thing is ROC of Z transform will always be in the form of circular strip. ROC will be always in the form of circular strip. So you have to identify a circular strip in the Z plane bounded by poles, bounded by these two poles, such that this ROC contains the unit circle. Okay, the only possible way is this one, this shaded region, right? This region includes the unit circle, right, as well as this region is bounded by these two poles, 2 by 3 and 2, and this is in a circular strip pattern. Okay, so this is the ROC, and that gives the answer to the question B. Okay, and question number C is to determine an ROC for x of n is left-sided. So consider x of n as left-sided. You have to determine an ROC for this left-sided signal. Again, you know, for a left-sided signal, all you need to know is that for a left-sided signal, ROC is inverse to the leftmost pole. Okay, ROC will be in a circular strip pattern, but that is inverse to the innermost or leftmost pole. Identify the leftmost pole in this pole 0 plot, which is the leftmost pole. It is 2 by 3. Okay, so you have to find out a circular pattern which is inverse to the leftmost pole, that is this circle, right? So I can draw it as so this area is the ROC for this left-sided signal because it is left to the innermost pole. Okay, or inner to the leftmost pole. Okay, so this is the answer to the entire question. Okay, let's move on to the next question. Determine the DTFS coefficients for the discrete time signal x of n equal to cos 2 pi by 3n plus sin 2 pi by 7n, and plot the magnitude and phase spectra. So this is a periodic signal, discrete time periodic signal. So we have covered so many problems like this where this is a clear case of method of inspection. Okay, method of inspection. So what I have to do as the first step is find the time period of the signal as well as angular frequency of the signal. angular frequency can be determined by omega 0 equal to, look at the argument of the cosine and sine. The numerator of the argument is 2 pi. Here is also 2 pi. So HCF of 2 pi comma 2 pi. 2 pi comma 2 pi divide by LCM of, again look at the argument, denominator has 3 and 7. So LCM of 3 comma 7. This is the general procedure to find out omega 0. Okay. So 2 pi and 2 pi HCF is 2 pi itself. Divide by LCM of 3 and 7. There are no common multiples, so 21, right? So 2 pi by 21 is the angular frequency. Therefore, what is the time period? Time period is n equal to 2 pi by omega 0, which is 2 pi by 2 pi by 21, which is equal to 21 samples. Okay, so we have got the angular frequency and time period. We have to save it for a later point of time. Okay, now, so this is the two results we have obtained so far. Now, in order to prepare the signal for the method of inspection, I have to write the signal as x of n is equal to, what is cos theta? Cos theta is e raised to j theta plus e raised to minus j theta whole divided by 2. So I can write as half e raised to j 2 pi n by 3 plus half e raised to minus j 2 pi n by 3. Okay, plus what is sin theta? Sin theta is e raised to j theta minus e raised to minus j theta whole divided by 2j. So I'm taking 1 by 2j common. So e raised to j 2 pi n by 7 minus 1 by 2j e raised to minus j 2 pi n by 7. So this is just application of Euler's theorem. We have done this in several previous problems. Okay. Now, let this be equation number 1. Okay, I'll keep it there. Now let me come to the DTFS equation. What is the actual DTFS equation? DTFS equation, by the synthesis equation, we can express any discrete time periodic signal as sigma over k equal to 0 to n minus 1. Okay, x of k, which is the Fourier coefficients, into e raised to jk omega 0 n. Okay, now coming to this particular signal, we have already found out what is omega 0, right? Omega 0 is 2 pi by 21. Okay, so I am rewriting this equation with respect to this signal whose angular frequency is 2 pi by 21. So this is sigma over x of k into e raised to j into k into, instead of omega, I'm writing 2 pi by 21, which is already we have obtained. Okay, into n, right? All right, now I am again taking equation number 1. This is equation number 2. This is the very important relation. We have to make use of it later. So now again taking equation number 1, where we have split our given signal in terms of exponents. Okay, exponents. Why did we split it in terms of exponents? Because we have to compare it with this standard equation of DTFS. It contains an exponential term. So that's why I have split this equation in terms of exponential. You know that. Okay. So equation number 1 can be written as x of n equal to half into e raised to j into 2 pi by 21 into 7n. Is that right? That should be right? Because if we cancel out 7 and 21, 2 pi by 3 remains. Here it is 2 pi by 3n. Okay, so I have actually, what I have done is I have multiplied with 7 on the numerator and denominator. That's why e raised to 2 pi by 21 into 7 comes. And do you know why did I do like that? Because in this equation number 2, we have e raised to jk 2 pi by 21. Okay, so in order to compare legibly, I have to take something e raised to j into 2 pi by 21 and a multiple in our equation for x of n. Okay, That's for just comparing, mere comparing. Okay, this is the first term, plus 1 by 2 into e raised to minus j into 2 pi by 21 into 7n. That is the second term. Here also I have multiplied 7 in the numerator and denominator and obtained 2 pi into 7 by 21. Okay, plus how can I do on the third term? 1 by 2j e raised to j into 2 pi by 21 into 7. No, it is already 2 pi by 7 here, right? So 2 pi by 2 pi by 21 into 3. That will give you 2 pi by 7 equal to 2 pi by 7. Okay, so e raised to 2 pi by 21 into 3 minus last term is 1 by 2j e raised to minus j into 2 pi by 21 into 3n. Here also n is there. Okay, so I have changed equation number 1 in this form. Okay, in the exponent I have multiplied by 7 in these two terms and by 3 on these two terms. Okay, now let us compare this equation with equation number 2, right? What we will obtain is we can deduct two things from this comparing. One is what is k in this term. If you compare this term, you can compare only this term and this term, right? Because this is a signal. E raised to j something into n is a signal, complex signal, exponential signal, right? So here also this is that signal, and whatever obtaining as the coefficient of the signal will be x of k. That's our strategy in doing this method of inspection, right? Okay, so what is k here? In this term, k is nothing but 7. Okay, so I can write first term corresponds to x of 7, right? X of k equal to x of 7. Okay, and what is that x of 7? You have to see that whatever be as the appears as the coefficient of this signal is this thing, whatever be the coefficient of signal, that is x of k, right? So that should be x of k in this term also. Here this is the signal, its coefficient is 1 by 2. Here this is the signal, its coefficient is x of k. So x of k equal to 1 by 2, and k is already 7 we have got. So x of 7 equal to 1 by 2. Okay, so x of 7 equal to 1 by 2. And similarly, what will you get from the second term? First, let us check what k this term corresponds to, and it's nothing but minus 7, right? It is not 7, it is minus 7, because we are comparing e raised to plus jk 2 pi by 21 with e raised to minus j 2 pi by 21 into 7n. So here k equal to minus 7, not plus 7. Okay, so we can write we will get x of minus 7 from this term. And what is x of minus 7? We can understand that whatever be appearing as the coefficient of the signal, that is x of k, right? So here coefficient of the signal is 1 by 2 again. So we can write x of minus 7 is equal to 1 by 2, right? So second coefficient is x of minus 7 is equal to 1 by 2. Similarly, what you will get from the third term? Third term corresponding to x of what k? Again, we are comparing with e raised to jk 2 pi by 21n. So e raised to j 3 into 2 pi by 21n. So k is obviously 3. K is obviously 3. So x of 3 equal to, and what is the value for x of 3? It is nothing but the coefficient of the signal. It is nothing but 1 by 2j. So 1 by 2j is the x of 3. And finally, from the last term, x of, what is k? K is nothing but, is it 3? No, it is minus 3. Here is a minus. Okay, so x of minus 3 will be equal to, what will be the value? It is the coefficient. The coefficient is nothing but minus 1 by 2j. Never miss the negative sign here. It will end up in wrong result. So x of minus 3 is equal to minus 1 by 2j. So we've got all the coefficients. Now the question asks us to plot the magnitude and phase spectra. So for the purpose of plotting magnitude and phase spectra, let me record this as mod x of 7 is equal to, listen, what is mod x of 7? It is 1 by 2 itself. And what is angle of x of 7? There is no e raised to term here, right? E raised to j0, we can write as e raised to j0. That means angle is 0. Okay, so angle of x of 7 equal to 0, right? So at k equal to 7, we can have the magnitude response as 1 by 2 and the phase response as 0. Now, what is mod x of minus 7? It is 1 by 2. And what is angle of x of minus 7? It is 0. Okay. So we got k equal to minus 7, magnitude response and phase response. Now, what is mod of x of 3? Mod of x of 3 is, we cannot include j. Okay, so 1 by 2. And what is angle of x of 3? It is actually 1 by 2j is actually 1 by 2j. For your information, it is actually minus j by 2. Okay, thus we are multiplying 1 by 2 by minus j, right? Multiplying by plus j means you are rotating a scalar by 90 degree counterclockwise. Similarly, what is multiplying by minus j? It is rotating by 90 degree in the clockwise direction. Okay, the clockwise direction 90 degree means it is actually minus 90 degree. Okay, minus 90 degree. So I can write 1 by 2 angle minus pi by 2, minus 90 degree. Okay, so we got the magnitude and the phase response for k equal to 3. And finally, what is mod x of minus 3? It is actually 1 by 2. Modulus is 1 by 2. You cannot find the you cannot take the negative here because we are considering magnitude response, mod x of minus 3. And likewise, what is angle of x of minus 3? You know, minus 1 by 2j is equal to minus 1 by 2 into minus j. J, if going to numerator, becomes minus j. So this is plus 1 by 2 into j. Okay, plus 1 by 2 into j means we are multiplying by j. That means rotating by 90 degree in the counterclockwise direction. That is taken as positive pi by 2. So the phase response at k equal to minus 3 is pi by 2. And magnitude response is 1 by 2. So with the help of these values, we are going to plot the magnitude response and the phase response. Okay. Okay, let's plot DTFS. But before plotting DTFS, there's a very important things to consider. That is DTFS has a particular feature. What is it? DTFS has a particular feature in frequency domain. DTFS is periodic. DTFS is periodic in frequency domain. So whatever we are going to plot in the frequency domain is periodic. Okay, that's a very important thing to consider before drawing the DTFS coefficients in a frequency domain. Okay. So what is the period in frequency domain? We have already calculated the period will be same as the period of the signal, and that was n equal to, I think it is 7. Right? No, n equal to 21. It was 21. 2 pi by 21 divided by 2 pi. So that was 21. Okay. So n was 21. Okay. So whatever we are drawing will be repeated after every 21 sample. Okay. So let's start drawing the magnitude spectrum. Okay. This is the magnitude spectrum I'm going to draw, mod x of k. Okay, so at this is k equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Okay. Similarly, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, etc. Okay, so we have x of 7 as half, magnitude is half. So x of 7, we have magnitude as 1 by 2. Okay, magnitude response. Now at x of minus 7 also we have 1 by 2. So x of minus 7 also we have 1 by 2 there. Now x of 3 is also 1 by 2. So at 3 we have the same amplitude, 1 by 2. Similarly, x of minus 3 is also having 1 by 2. So x of minus 3, 1 by 2. Right? So this is the magnitude spectrum, and I'm going to tell you that this is going to repeat after every 21 samples. Okay. So since there is no space here, I cannot visibly mark it. So we have to assume that this entire spectrum repeat after every 21 sample. Okay, so I can write it here for your reference. This spectrum repeats. This spectrum repeats after every 21 sample. Okay, because n equal to 21 here, that's the reason, right? So this is repeating. And now let us draw the phase response also. Phase response, okay, one second. Okay, so this is the phase response. Again, this is being drawn for k values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. in the positive side, and -1, -2, -3, -4, -5, -6, -7, -8, etc. in the negative side also. So this is angle of x of k I'm going to draw, which is the phase response. We call it phase response. Okay, marking some plus pi by 2 here and some minus pi by 2 here. Okay. Now, what is the angle at k equal to 7? It is 0. So at k equal to 7, we have 0, right? Now, what is the angle at k equal to -7? That is also 0. So at k equal to -7 also, we have 0 phase. Now, what is the phase at k equal to 3? It is minus pi by 2. Half angle minus pi by 2 means the phase is minus pi by 2. So at k equal to 3, we have a negative phase. Okay, negative phase of pi by 2, negative pi by 2. Right. Now, what is the angle at k equal to -3? It is angle is equal to plus pi by 2, right? Plus pi by 2. So at k equal to -3, we are having a positive phase, positive pi by 2. Okay. And again, this entire thing, I have to say, this entire thing repeats after every 21 sample. You have to take note of that. Okay. So this is the answer to this question. So here comes the next question. Consider an LTI system characterized by the input-output relation given a difference equation. Question A, compute the system function h of z. Question B, sketch the possible ROCs for h of z. And the last one, compute the impulse response h of n if it is known that the impulse response is left-sided. So let us start with the difference equation. And the question A asks us to compute the system function or transfer function h of z. Okay, so in order to compute transfer function from the given difference equation, you have to take the z transform on both sides of the difference equation. Okay, so taking z transform on both sides, of the difference equation, y of z, okay, y of n has transform y of z minus 1 by 4 into y of n minus 1 will be having z transform z inverse into y of z owing to the time shifting property of z transform equal to, now apply z transform with the RHS, you will get x of z plus 1 by 6 into, again it is time shifting, so z inverse into x of z. So this is what you will get if you apply z transform on both sides of this difference equation. Okay, so I can take y of z common in the left hand side, so y of z into 1 minus 1 by 4 z inverse is equal to, I can take x of z common on the RHS, 1 plus 1 by 6 z inverse. That will give you the transfer function, which is the ratio of output transform divided by input transform, and that will be 1 plus 1 by 6 z inverse divided by 1 minus 1 by 4 z inverse. So this is the answer to the question A. Answer to the question A. If you have computed the system function h of z. Okay. Now question B asks us to sketch all the possible ROCs for h of z. Okay. So how can you plot the ROC? Here, so okay, for plotting the ROC, you have to draw the z plane and mark the unit circle and mark the circle corresponding to the pole of this transfer function. What is the pole of this transfer function? This transfer function is actually having same degree, so it's an improper transfer function. Anyway, whatever it is, that's not relevant to our analysis now. So this is having a single pole which is at z equal to 1 by 4, mod z equal to 1 by 4, right? Because the denominator equals to 0. Pole means, you know what a pole means, right? Poles are those values of denominator which turns it to 0. So z equal to 1 by 4 is a pole, is the only pole of this transfer function. Okay, so I can mark or draw the z plane and mark this pole. Okay, so this is the pole 0 plot of this transfer function. I have omitted zeros because that is not relevant to this question now. The pole is at z equal to 1 by 4. So I have drawn a circle in yellow color which corresponds to this pole at z equal to 1 by 4. Okay, mod z equal to 1 by 4 is the equation of the circle. And I have drawn the unit circle. Okay, fine. Now the question is to sketch the possible ROCs for h of z. So what are the possible ROCs? If at all this signal is right-sided, right, there are two conditions. Either the signal may be right-sided, the signal means h of n, the inverse transform h of n, maybe it is right-sided or it is left-sided. Okay, if at all this h of n is right-sided, then what will be the ROC? How will be the ROC? The ROC will be outer to the outermost pole, or here the pole is just z equal to 1 by 4. So the ROC will be outer to the outermost pole, or the pole. This is single pole. So this will be the ROC. Okay, so we can write that ROC will be right-sided. If it is right-sided, mod z greater than 1 by 4 is the ROC. So this is one possible ROC. Okay. Now there is one more possible ROC when the inverse transform or h of n is left-sided, right? Left-sided. What is the nature of the ROC if this h of n is left-sided? It will be inner to the pole. Inner to the innermost pole is the exact answer, but here there is only one single pole, so inner to the pole. So I can draw the ROC as this thing. This yellow colored circle is the circle corresponding to the pole. So the ROC, if at all it is left-sided, it will be inner to the innermost pole. Okay, so this is the second possible ROC. And I can write the equation of ROC as mod z less than 1 by 4. This is the second possible ROC. This is the first one. This is the second possible ROC. So that completes the answer to question number B. And the last question is, compute the impulse response h of n if it is known that or given that impulse response is left-sided. So the questioner has given you that the impulse response is left-sided. Okay, left-sided. So in that case, what will be h of n? You have to find out h of n. So to do that, let us consider the h of z. I'm rewriting h of z. We have already found out h of z here, right? I'm rewriting it. H of z equal to 1 plus 1 by 6 z inverse divided by 1 minus 1 by 4 z inverse. Straight away, we cannot apply any inverse transform rules to get h of n. So what I'm doing is, I'm splitting this fraction to 1 by 1 minus 1 by 4 z inverse plus 1 by 6 z inverse into 1 by 1 minus 1 by 4 z inverse. Okay, this is same, right? Now apply inverse transform, inverse z transform. That implies h of n. H of z will give an inverse transform h of n. So h of n equal to, what is the inverse transform of this function? This is a non-standard one, right? Because inverse transform of 1 by 1 minus a z inverse is equal to a raised to n u of n. You know this. Okay. So making use of this standard result, I am writing it as 1 by 4 to the power n u of n. That is the inverse transform of the first term. Okay, plus there is a constant 1 by 6. So according to linearity, I can write x, okay, 1 by 6. Now you can see in the second term that there is a term 1 by 1 minus 4 1 by 1 minus 1 by 4 Z inverse into Z inverse. So what is the inverse transform? If at all I'm considering this term alone, 1 by 1 minus 1 by 4 Z inverse alone, we know its inverse transform is 1 by 4 raised to u of n. But if Z inverse into some x of z is coming, right? Z inverse into x of z is coming, then what is the inverse transform? We can make use of time shift property, right? X of n minus 1, and x of n minus 1 will be the inverse transform of z inverse into x of z. This is straight away property of time shifting property. Okay, so I can write 1 by 6 into inverse transform of 1 by 1 minus 1 by 4 z inverse is 1 by 4 raised to n u of n. So I can write 1 by 4 to the power n minus 1 u of n minus 1. Okay, so this is the impulse response, assuming that the signal is right sided, but you're given that the signal is left sided. Okay, left sided. So we have to change this signal, this impulse response, that implies to be left sided. Left sided h of n will give you h of n is equal to both the terms should be left sided. So minus 1 by 4 to the power n u of minus n minus 1 plus, right? That is how you change a right sided signal into corresponding left sided. You have to add a minus sign here, and you cannot change 1 by 4 raised to n, that is the damping of the signal. You cannot change it, and u of n is to be changed into u of minus n minus 1, because u of minus n minus 1 represents the left sided counterpart of u of n. Okay, plus what about the second term? Second term is 1 by 6 into 1 by, okay, it is not plus, you have to add minus, right? Plus minus 1 by 6 into 1 by 4 raised to n minus 1, you cannot change it. Now how will you change u of n minus 1? For that you have to find, you have to take note that it was u of here it was u of minus n minus 1. Okay, u of minus n minus 1 because the index were n here. Okay, but now it is n minus 1 here index, so we have to find u of, actually what we need to do is u of minus n minus 1, like this term, but here it is, index is 1 unit shifted, so u of minus of n minus 1 minus 1. Okay, that will give you the final result, h of n equal to minus 1 by 4 to the power n u of minus n minus 1 minus 1 by 6 1 by 4 to the power n minus 1. This will be u of minus n plus 1 minus 1 is u of minus n. Okay, so this could be the final answer, the impulse response when the signal is left sided. Okay, so that completes the answer.